we are ready to move on to Mr. Hiromatsu's presentation. Mr. Hiromatsu, are you ready for your presentation?
Thank you. Can I share my screen now?
Okay,
Right?
yes.
Is that
Okay, I
right?
think we are good. Yes.
Okay,
All
good.
right, so next up we have Mr. Hiromatsu. Mr. Hiromatsu, please.
Okay, thank you. My name is Koichiro Hiromatsu from Mitsumekan High School, and I'm glad to be presenting here today. Thank you for the opportunity. The title is The General Linear Model, Statistical Analysis for Inquiry and Research. So basically, I want you guys, everyone to remember the name here, the GLM, the General Linear Model, which is kind of popular, but maybe not so popular. I don't know if you've heard of it or not. Has anyone heard of this before? The general linear model? No? Okay. Good. So it's going to be new. And what it is I want to propose a new way to teach statistics that is more for inquiry, that should work better with um, inquiry-based learning or research, and also I think easier for students to understand. So let me start. So today I'll give a self-introduction and then talk about statistical education in Japan, and then get on to the GLM. So first of all, my name is Koichiro Hiromatsu. I was born and raised in Texas. Lived there for 18 years, and I took AP Stats as a junior. This was my first. Oh, the picture. Yeah, don't worry about that. So when I was 17, I had my first introduction to statistics when I took AP Statistics, and at the time, which was 1999, right? Um, it was pretty a basic run-of-the-mill AP Stats course. We did t-tests, chi-squared, learned some basic things, hypothesis testing, things like that. And I ended up going to Reed College in Oregon, studied math there, but I didn't take any statistics courses when I was at Reed College. So there's been a big blank in my statistics learning. And then I moved to Japan when I was 22. I was teaching English for about 10 years, but I wanted to teach my first love, math. And so I went to university in Kyoto, got my math teaching license, and I've been teaching math at Ritsumeikan for about 10 years now. And even then, I didn't teach much statistics, but I think it's when I was helping instructing students' research projects that I realized the necessity for a statistics education or data science, might even call it that. And so it really got me thinking and got me studying again on my own about statistics, which had me come up with this idea of what statistics education should be, or a good, not should be, but one proposal. So in Japan, how have we been teaching statistics? So in 1977, before I was born, there was a reduction in school hours, and but they still had a probabilities and statistics course. But more and more as Japan kind of went away from the hardcore entrance exam. I mean, there still is a big university entrance exam culture here, but they kind of went away, tried to not to teach too much, and they started there were less school hours and less content. And in 1989, there was a big reduction in statistical content, and it was just basically descriptive statistics, mean, median, mode, not doing any inference, which you would need for inquiry usually. And in 1999, they brought back some inferential statistics, but it was elective and many people didn't take it. In 2009, even more statistics came back, but it wasn't on the natural entrance exam. So a lot of schools weren't interested in teaching it. So it wasn't emphasized very much because many people are just aiming for the exam. So if it's not on there, you're not going to teach it very much. But in 2018, recently, there was a strengthening of both descriptive and inferential statistics, and it was now part of the national exam. So people had to learn it. And so I think that's kind of come back, and a lot of math teachers are kind of worried because they didn't really study this themselves. But now it's on the entrance exam, so they have to teach it. But so the current curriculum in Japan, so in junior high school, you do some easy stuff, frequency distributions, what is sampling, learning about box plots, or I suppose you might call them box and whisker plots. And then in grade 12, in math 1, you do a little bit of data analysis, learning mean median mode, the variance, standard deviation, correlation between two variables, an introduction to hypothesis testing. And I put least squares in italics because it's not required. And I think most people don't actually do it at different schools. Do people here have you heard of the method of least squares? Okay, great. So, great. I mean, you haven't. So, some have. Good. I can't really see everyone, so let me try to have it on my iPad over here as well. See it. All right. And then in math 2, nope, that's actually wrong. So please correct this later. Math B, it's in grade 11. It's called Math B. There's inferential statistics with a random variable, probability distributions, estimation. This is new, using confidence intervals, 95% confidence intervals, and hypothesis testing. But they only use the z-test, which is the most basic of tests and not very useful in most research. So it's kind of a very academic pursuit here. All right. Although information science, which is a different from math, they actually do some statistics stuff, some data science things in those courses. And information science 1, it is on the entrance exam, so I think most schools teach this. But simple stuff, interpreting the mean, what is the standard deviation? It's more about interpreting the statistics rather than doing the calculations or the hard, the proofs or anything like that. Information science 2 is usually in grade 11, but it's not required and most schools don't do it. But apparently they do regression analysis, clustering, things like that. That's more conceptually based. All right, so that's the kind of situation in Japan for now. But in my personal opinion, I think there's not enough conceptual understanding for the students. They just want to, pass the test and figure out, tell me the formula. How do I need to do it? Then I can pass the test. The content is not so practical. So like I said, we only teach the z-test in math, which is not the most common test used in most research, I don't think. You're more likely to use a t-test. I also don't even teach p-values. So you see that a lot in research, and students won't have a foundation for that. And there's not much ICT integration, probably going back to testability, because students can't use their computers on a test. So here comes my proposal. I want to do the general linear model approach, the GLM. So first of all, what's the traditional statistics approach? For example, if you wanted to find out how are height and arm length related, you would a lot of people measure their arm length, measure their height, and you'd probably do a simple linear regression if you think there's some linear relationship. You look at the coefficients, you'd say, oh, okay, there's the slope, there's the y-intercept. You'd also perhaps look at the correlation coefficient or the coefficient of determination. Sorry, I haven't said it in English in a while. Sorry. So that's okay. That's fine. Next, what if you're interested in, does eating chocolate help lose weight loss? I'm interested. Right. But so, for example, you have a group of students who do eat chocolate and a group of students that don't eat chocolate, and you want to compare the sample means. So you do a 2-sample independent t-test. You look at the p-value, you might want to check out the effect size, okay? Or how about if you have more than 2 groups, the type of soil affect plant height. So you have 3 different types. This time, you can't use a t-test, you need to use a one-way ANOVA and then do a F-test. And then we're going to have post hoc tests with lots of multiple comparisons, one-on-one. So it gets very complicated. And for students end up seeing something like this, where, okay, how many predictors do you have? Are they numerical? Are they categorical? You have to think of all this, and then you have to choose the right test. So if you want to do, if you have one predictor that's predicting, one on the x-axis, one x independent variable, and there's 2 or plus groups, you need an ANOVA. If there's more than one predictor and there's a mix between numerical and categorical, you're going to need an ANCOVA. But how do you do that? You have to do it all again from scratch. So this is very complicated. I think students get lost in choosing which test or trying to understand which test. They just want to test it, And so I think this is very confusing for students, and it's not, doesn't help them conceptually. That's where the general linear model comes in, because it can do all these tests in one framework, which is easy to understand, I think. Easier to understand than the original tests. So what is it? First of all, before you go on to the general linear model, I'd like to talk about the linear model, which is just linear regression. You model a relationship with a line. So for example, like I said before, arm length and height. You would make a model like this. You can have a model equation here. So y equals a plus bx. That's your model. But of course, the actual data doesn't fall right on the line. There are some residuals. There's some error in your measurements, right? Just because you know someone's arm length doesn't determine 100% their height, right? You're always going to, some people are, you model it, but they could be taller or shorter. There's residuals, okay? So this is a linear model with a model part and the residual part. This is true for everything I'm going to say from now on. But usually, so in normal math classes, we have a plus bx, but in the general linear model, we usually write it like this. There's different coefficients. The intercepts will be beta 0, and then the first coefficient beta 1. Okay, that's just how they write it. Not a big deal. So just remember that. All right. So how do you find out which line is the best model? So how do you find the best fit line? And this is where a very common term, the ordinary least squares. So we want to find the line, and what do I mean by find the line? I mean, we want to find the parameters. So B0 and B1, or in normal math terms, A and B, or slope and intercept. We want to find the best slope and intercept, which minimizes the square of the residuals, the square of the error. So we want less error. Although we can't just say add the error up, because some are positive, some are negative, and they cancel each other out. So you square all the terms, and you want to find which slopes and intercepts minimize this. All right, so for example, if you just draw a straight line in the middle on the left side, you can see this is set the average. You have huge error terms, the red lines. These are how far it's off from your model. But if you use the blue line on the right, the error terms, i.e. the residuals after you've modeled it, you've predicted with your x values, you predicted the y values, how far off are you? These are much smaller. And so if you square them, add them up, that total, and here it says SSR, that's sum of squared residuals. It's much smaller. So you want to find the best line that has the smallest SSR. All right, so I'm not going to go through how to do that. It's not difficult, but I don't have time. And so if I do this in Python, it'll shoot out this very complicated looking output. But we don't care about all this stuff. We just care about these parts here. The R squared, that tells us how much of the variance or the variation in your data is explained by the model. Okay, so this is higher. It means you have more explanation power with your independent variables. P-value, that means how significant is your model, statistically significant. If this is very low, it means, oh, it's probably not due to chance. If it's high, you could say your model, it's just chance. It's not actually significant. And on the bottom part, this is just Python output. It gives you the coefficients, which we are looking for, the parameters, beta 0, beta 1, fit using OLS, which is ordinary least squares. And for each coefficient, you get a p-value and some confidence intervals. Great. So is your parameter useful or not? Maybe. That's an easy way to think about it. All right. So there's also one more output I want to point out. There's something called an ANOVA table. I'll just go through quickly. This tells you, for example, arm length. The variable arm length explains this much variance, 1,234. And there's still 1,946 variance left. What is that? I won't go into it, but just know that that explains the amount of variance explained. And you get a p-value. Okay, so this is just normal linear regression, a linear model. What is a general linear model? Well, this linear model can be expanded to, for example, categorical data. So you want to compare teaching methods, okay? How would you do that normally? Normally, you would use an ANOVA, analysis of variance, because you have more than 2 groups. And after that, you do post hoc studies. But here, all I do is I give it these variables. For example, there's a few ways to do this. One way is to call x1, it's 1 if it's data from teaching method A, and everything else is 0. X2 is 1 if you're using teaching method B, otherwise it's 0. And X3 is teaching method C, else 0. So if your teaching method is A, you'll notice that the beta 1 remains and the beta 2 and beta 3 are gone, right? So they disappear because your X2 and X3 are zeros. So that means if your teaching method is A, you get Y equals beta 1 plus an error term, right? Which means beta 1 should be your average for teaching method A. So that's how you can interpret these coefficients. And beta 2 would be your average for teaching method B. And using this, you can run it through the process. I'm going to show one more, just because this is one way to do it. There's another way to do it that's kind of more common. There's a difference, but I can't get into it now. Sometimes they encode the variables like this. So x1, if you're using teaching method B, it's a 1, otherwise 0. x2, if you're teaching method C, it's a 1, else 0. Okay, so if you're using teaching method A, that means x1 and x2 are 0. So B0, that first term, that's your average for A. And if you're teaching method B, you get B0 plus B1. So what is, not B, I'm sorry, beta. Beta 0 plus beta 1. So what does beta 1 mean in that sense? In that sense, in that model, the beta 1 would be the difference between method B and method A. So how much do you have to add to A's average to get B's average? So this is a very common way of encoding it. But as you can see, the model here, the model equation, looks very similar to the original linear model, right? Which students are very familiar with. You have A plus BX, things like that. So it's the same setup. And it'll give you this kind of output. And you see, I want to look at the parameters here. We get beta 0, beta 1, beta 2. It doesn't say that here. It says here intercept, teaching method B, teaching method C. The intercept is B0, beta 0, which is the average for A, right? And beta 1, this is the average for B minus the average for A. So you can see that the average for B is 5.5 points higher than average for A. And the teaching method C is negative 1.39 points higher, so lower than average for A. But if you look to the right, you can look at the p-values. We're going to ignore the intercept for now, but for teaching method B, the difference between B and A, the p-value is 0.006, whereas the difference between A and C is 0.476. So it's not a significant difference here, as you can see. Also, you can look up here the R squared. This means by knowing the teaching method, you're able to explain about 14% of the variation in your test scores. And the probability, this is the p-value for your whole model, would be 0.001. So it's a significant model, statistically significant. It's probably not chance. Okay, so my point is here, you can use categorical variables using, go back, using this kind of equation, which looks just like the other one. So this is a linear model, but now it's fitted for categorical variables. So you can do a t-test comparing two groups, or three groups, or four groups, or five groups. You just add more variables in. And it's a very simple process. You just add in variables. So this, I think, could be useful. So, okay, that's not it. You also get polynomial regression. This is very easy to do. All you do is add the x squared variable. So, for example, you're modeling the height of a ball as a quadratic. So your model equation here is a quadratic. You want to fit that model after dropping from a height of 10 meters, all right? And we're still going to use ordinary least squares, which says minimize the square of the error term. Minimize the sum of the squares of the error term. Okay, so we fit the model, and we get the parameters here on the left side. This is how you read it. The beta 0, beta 1, beta 2 would be the intercept time and time squared. So the intercept is 10. What does that mean? It means that time, if x is 0, if time is 0, you should be around 10, 9.999. Okay, it's not exactly 10, but pretty much 10 meters. You start at 10 meters. The time, the x term, is negative 0.17. That's fine. But the p-value is 0.447. So this is a very high p-value, which means not significant. So the x term is not so significant. The x squared term is very significant, 0.000, and its coefficient is negative 4.8. So I think most physics teachers would know that, of course, it's gravity. You should be falling at, negative 4.9 x squared. So this is pretty close, right? Negative 4.9 x squared, is that right? For physics teachers out there. All right, so you can easily do polynomial regression using this as well. And you can see the R squared. You've explained almost all the data is, and so you can fit this kind of curve using a general linear model, which is just, it looks exactly like a linear model, but you just have more terms. All right, I keep going quickly. I know I don't have much time, right? So multiple explanatory variables. You want to have multiple variables explaining your or predicting some other variable. So for example, you do a biology experiment trying to find out what affects plant height. So you change the amount of water, change the amount of sunlight, and the average temperature. And here you have three variables. And you just plug them all in. You give three variables to the model equation and put your data in through Python or R or whatever software you're using. And you get this kind of output. So you say the intercept, which means if all the x's are zeros, so what does that mean? Your temperature is 0, your water is 0, and your sunlight 0. That's not very meaningful, so you don't usually interpret that very much. But okay, the water amount, the coefficient 2.7. So if I increase water by 1 unit, the height should also increase by 2.7 units. Oh, okay. Sunlight and temperature. But notice on the side here, it gives you the p-values for each coefficient, or for each variable, or coefficient, yes. This temperature one is not significant. So maybe temperature is not important to plant growth. Of course, this is fake data. I mean, it could be. Please, biologists, don't attack me. This is fake data, but in this data, the temperature was not significant, but the amount of sunlight and water was. Okay? And you can see here, same thing. I'm not going to go through this just in terms of time. But yeah, you can just add more variables very easily. I'm interested in this variable. Okay, add it to the model, see what happens. And here's an interesting one. controlling for confounding variables. I read about this when I was younger. In America, apparently there was something going on saying that women get 77 cents to the dollar or something like that, right? And compared to men, I thought, wow, that's pretty hard. Because there's the law saying you can't discriminate based on sex. I thought, wow, what's happening? And I read up on it. And so this has to do with that. Of course, this is, again, fake data. I just made it up. So for example, you look at everyone's yearly salary and then you model it based on the gender. So X1 is 1 if it's a male, 0 if it's a female, which means beta 0, beta naught, is your female average. And beta 1 is the difference between male and female. That's how this is going to be interpreted, right? So let's run it through this model. And you get a R squared of, 11%. Fine, that's fine. Over here, you got 11 R squared, 11%. 11% of your variation in yearly income is explained by gender. Okay, fine, your data. But if you see, okay, down here, the gender coefficient is very significant and it's very big, right? So you might come to the conclusion that, yeah, this is very important. It's hard to read this because it's all in scientific notation, but the intercept, for example, the female yearly income is $100,000 and the male is $2,000 more. So it's like, wow, okay, yeah, they're making a lot more than it. And that's what it looks like. But for example, this is just a made up example, so don't worry. For example, what if you add to the model age, the number of hours you work per week, and the job level, maybe your entry level, mid level, or your CEO or something like that. You can, and these are mixed with categorical variable. This has numerical variable. It's all mixed together. But you could just add those variables to the model and run it again. And what do you get? So you get a very, let's see, if we're comparing the models, on model 1, you only use gender. On model 2, you have all these factors put in there. And you can see a higher R squared, of course, you're explaining more of the data because you have more variables to explain it with. And on the bottom, this is interesting. So the gender, if you look at the p-value, now it's 0.84, which is not significant at all. The job type is very significant. Age is very significant, and the time you work per week is significant. And I didn't talk about this part very much, but if you can see here, this tells you how much. This is called a ANOVA table, but this tells you how much of the variation is explained by each variable after oh, what's what I'm looking for? After all the other after all the other variables have been used. So if I model using gender, job type, age, and time, then time worked per week can explain this much of the remaining variation a lot. But for example, if I tell you the time worked per week, the age, and the job type, and then I say I've controlled for all these different variables, how much does gender explain? Well, it's very small compared to the other ones, which is a very not significant. So this is just an example that I read many years ago. I was like, oh, that's very interesting. So the problem isn't that people are actually paying some men and women for the same job, different income. It could be that the problem is that women aren't in the same jobs, or maybe they don't get the same, what do you call it, positions. So it's just you might be missing what the actual, the real reason is, or there's a confounding variables that makes you come to the wrong conclusion. And I think this would be interesting for students who want to do this sort of thing, but don't have the ability or the tools to do it. This can give them tools to kind of add in other variables that they want to control for very easily too. You just add it into the model. I'll just have one last thing to say. I think I've gone past my time, sorry. The summary, why the GLM, it unifies multiple methods into one framework. It also, you have to think more about concepts and how to interpret the results rather than calculations. You can also do more deeper inquiry like confounding variables. I didn't talk about today, but interaction effects, very easy to add. And you also, number 4, you learn how to compare models to figure out what model do you think best suits your data, and you have to think critically about it. Also, I didn't mention it today, but there's many more advanced topics that build off the GLM. Mixed models, you can also move into machine learning, and more. So I think this is a great way to introduce statistics to students instead of using the traditional approach. References, more like recommendations. I think these YouTube channels, StatQuest is amazing for people that are, students or your first time trying to understand the topics. Simplistics is a little more complex, well, a little more in depth, but these 2 channels have been great for me for learning. Also, the book called Modern Statistics for the Life Sciences. It shows how to do biology or life sciences using the GLM. So if you're interested, I recommend these. That's it for me. Sorry, went over.
Thank you, Mr. Hiromatsu. I'm wondering if we have questions from the audience before I pitch my question, because he picked biology examples. We have math teachers online, I know. Let's see. Wait time is important.
Math teachers in Japan aren't excited about teaching statistics. I think it's true for a lot of math teachers, because a lot of math teachers find it to be kind of, a different type of math. But I enjoy it. Yes.
Okay. I'm going to ask my 2 cents worth.
Okay.
So, major disclaimer, I'm a biology teacher, so I am not very good at math, but I do mentor students on projects, and one of the aspect of the biology curriculum in Singapore, we actually do just one statistical test. No, actually we do 2 statistical tests. We do the chi-square model, which essentially compares your observations with an expected model. So we use chi-square test for that. And then we also introduce the t-test as to compare whether the means are significantly different. So that's what I understood. Earlier on, I'm very curious because I know that you put in fake data for this. I'm just wondering, is this a method for the students to analyze, assuming that they still set up their experiment? They need to take their experiment somewhere, right? Say, for example, if you go to the example of the sunlight and whatever not. Yes, this one. So do I understand it correctly that I imagine I have a student group, and then their measured dependent variable is plant height. And then they must have had some data working with some groups manipulating water, and then they measure the plant height, and then some other groups manipulate only the sunlight, and then they measure the plant height. And then after that, using this model is able to kind of give them information that tells them which factor affects the plant height more. Do I understand that correctly?
So this would be, for example, plant height. You have that data, and you also have the amount of water and the amount of sunlight and the average temperature that resulted in that plant height. So that would be one set of data. Like, you wouldn't do it separately. So you have like a row of x1, x2, x3, and y, and you have a bunch of those data points, and then that's what you would use to fit the model.
Mm,
So you could
okay.
record. So for one plant, you could record the amount of water, record the amount of sunlight, record the average temperature, and in the end, record the plant height, and that would be one data point. And then you
Oh,
could have multiple data points to fit the data, fit the model.
oh, that sounds interesting because then it feels like I don't need to set up so many
I
experiments.
know.
Uh,
Yes, exactly.
and I kind of mixed up the various data points and I try to to
Right.
model this.
Exactly. I
Okay,
think
maybe we
this.
should play with one of the student group this year for the research project.
I agree. Can I say two things about that?
Yeah, please.
Um, One thing is that this is very good for. I know scientists, science teachers know this as well, but when you're doing hypothesis testing, you should only focus on one thing.
Yeah.
And that's true for this as well. It looks like I'm looking at a lot of things and testing a lot of things all at once. That is not a good idea. But this is good for exploratory data analysis. So before you've made your hypothesis, this
Hmm.
gives you a lot of insight into it. And then you can actually use this to do, if you only
Develop
focus on one,
hypothesis.
yes, develop a hypothesis. Exactly. And the other thing is, you still need to worry about experimental design. Your data points need to be independent. You can't have like this using the same soil for these three and a different soil for another three. That requires different methods. You still have to have independent data points. So teaching experimental design still holds in this situation.
Mm-mm. That's interesting. So that's something new that I've learned from this session, although I struggled very much with the equations.
A lot of
But
math.
thank you. Yes, it
Yes.
is, and it's many algebraic symbols.
Yes.
Okay.
Trust me,
Yeah.
it's less than this traditional techniques.
Oh, okay. What about the other members in the audience? We have math teachers. I imagine we have non-math teachers. Do we have questions for our statistic expert here today? Questions? No questions? Shocking is muted. Okay.
Hi. Yeah, thanks for the sharing. It's really mind-blowing. Even though I'm a math teacher, we do teach statistics, but we don't do the stats that you were just explaining earlier. But I'm very keen to understand how do you define p-value for
Uh,
the test that you have done?
okay. There were two types of p-values that showed up. One
Mm,
was a p-value for the f-test here for the whole model. And
mm,
then you have p-values down here for each coefficient.
mm.
Uh, and this is for the f statistics, it's, do you do f-tests?
Actually, we don't. It
Right.
has been
Yeah.
taken out since don't know how long ago. Yeah.
Yeah. Yeah. Uh,
Mm,
I can understand why, because it's a bit, if you want to teach it very rigorously, I think it would be very difficult for most students. But the F statistics is basically saying, um, by explain with this kind of model, the kind of fit that you got, what is the chance that you got it by chance?
mm.
That given that there is no that your model is completely wrong and there's no relationship, what is the
No
chance that
correlation.
right.
Mm.
There's no correlation. What was the chance that you would have this kind of correlation in your data, given that there was actually no correlation in the what sort of population? And so in that case, for this model, it's very, very small, which means that um, that this model is probably not, you didn't probably just, it's probably not random. It is probably a significant correlation. And then the bottom, these are t-tests against the slope being, or t-test against the what do you call it, the null hypothesis would be that the intercept is 0. And here, the null hypothesis is that the slope is 0. And you're doing a t-test on that. And there's the t-tests for these are a little different than the normal 2-sample independent t-tests, where the standard error is defined a little differently than differences. But basically, it's a t-test against the null hypothesis that these coefficients are 0. So 0 is 0.000 means, of course, if the slope is 0, that means that your x variables have no correlation with the y's. It's no effect at all. And so here it's saying, oh, okay, given that there were no effect, that arm length cannot predict height, the chance that you would get this kind of coefficient would be 0, almost 0. So it's a significant relation or correlation. And for intercept, it doesn't make much sense. It's saying, what's the chance that even though the actual intercept is 0, you would get an intercept of 81.74 or larger, which is not very interesting to us because we don't really think that the intercept is 0. So, but yeah, basically, if this were just chance, if there were no actual effect, what is the chance, or what are the probability of us getting this kind of data? Or yeah.
So okay, thanks for the explanation.
Sure.
I'm still a little bit confused because I'm like trying to wrap my head around how to interpret the p-values. But I'm just wondering, because a lot of all this data seems to be fed into some software, right? The software, the Python, right? You were using Python.
Yeah. Yes.
So so again, when a lot of all this data is fed into it and certain results are thrown out, how do we, or how do you ensure that the students truly appreciate all these values, rather than, oh, I just pick it, and when you say that, oh, if it's small it means this, if it is big it means that, okay, I can make the conclusion. But how do we teach so that students truly appreciate the meaning behind all this, the magnitude of all these numbers?
I think that's very difficult, but something that's very important, because from what I hear, I'm not a researcher, I'm a math teacher, but from what I hear is that in research, a lot of people don't know how to interpret p-values, and you end up with things called like p-hacking or harking, and there's a misuse of p-values, which ends up with bad research ethics. And I think it's very important that students understand what it means, not just low p-value equals good result. That's something that they really need to think. So I think one thing that's good here is you have R squared and p-values. R squared is normally used as effect size. In p-test, you'd have like a Cohen's D or glass G, Pleasance G. There's lots of different effect sizes. And I think a lot of people don't realize that a p-value just tells you how sure you are that there is effect. Whereas effect size says how big the effect is, which is sometimes more important. So you could be sure that, if I sleep 10 hours every night, it definitely has a big effect on or not a big effect, a low p-value for increasing my test scores. But it only increases it by 1 point. So you don't want to conflate p-values, which means significance, with actual size of the effect. And so I think going with students through concrete examples and then having them think critically about it as well, and how could this, a low p-value, actually, how could it be wrong, or what mistakes could we have made? Go through that with them and make them think critically about each one as you go through it, as well as interpreting it as well. But yes, I think p-values is one thing a lot of students suffer with interpreting, because it's not super easy to understand. It's a bit of a, what do you call it? You're using reverse. Sorry, the Japanese is coming up, but not the English. It's not an easy thing to understand. So I think going through it and explaining it, or having them express what they think it is, and then you kind of giving feedback. These things are pretty important, I think. I don't know if that was your question.
Right. Thank you, Xiaoqing, for the question. What about any other questions? This afternoon we have an M-Week teacher.
Oh.
Any comments, thoughts from you? I can't really hear you.
Mic is not.
The mic is off, but then can't hear the volume. Would you like to try unplugging your earphone from the computer? Maybe then we will be able to catch your voice. No? Hang on. Is she muted? Hang on. Cannot hear. No. Try again. Unfortunately. No. We cannot hear. Well, but if you have question, you can type in the chat. Maybe that would work. I'm not an expert at troubleshooting Microsoft Teams. Right? No response. Well, while we are waiting and to see, Mr. Hiromatsu, I'm wondering, are you proposing to teach this to your students who are taking up research projects?
Oh, actually, from April, we're we're developing a new elective course called Data Science here at Ritsumeikan High School. It's an elective course, and I'll be running it, developing it, and we're going to do a lot of this kind of. We're going to use the general linear model as a base to do inquiry kind of research, data analysis. So hopefully in a year, I'll be able to give you some good feedback, or yes, and how it went. Also, yeah, for any of our students that want to use this for their research, because we all do research projects, I don't know if I'm going to teach this to them, because it would take a little while. It has to be kind of structured to go through it. But I want to be able to hopefully, teach it to the students that need it. And yeah. But yeah, so we're going to start a new course, an elective course. Hopefully. Interesting.
Okay. All right. I'm mindful of the time because the time is quite advanced over in Australia.
Oh, yes, yes.
Yeah. I'm wondering if there are any other general comments, questions from everyone. Yeah. I think Mr. Hiromatsu, the M-Week teacher, says that she would like to, she's going to share with her M-Week colleagues.
Okay, great. And I don't know. Here, I'll turn this off real quick. I can't print.
Yes.
If anyone wants the slides or something, you can always contact me at.
Yeah.
Here, I'm going to give my email in the. Yes, there it is. There's no S. Be careful. It's not Hiromatsu. It's Hiromatu. You have to be. They only gave me 8 letters for the mail address, though.
Okay.
Yeah. So I had to cut one, and so
All
very
right.
cute. Hiromatu. Yeah. So if you need anything, if you want to see the slides again or something, give it to me. Give me an email.
Okay. All right. Thank you for the sharing. Thank you everyone for joining this session. I think with the math loading on the head, and then earlier on we had a very dense science and authentic context using using context for developing tasks. That's quite a bit of learning today. So I think I would make the move to draw this session to a close. So thank you everyone for participating in this particular session. Uh, Takeda sensei. Okay, thank you
Thank
and bye
you.
bye.
Thank
Thank you. Bye
you,
bye.
Shen. Bye bye.
Thank you, everyone. Thank you.
Thank you. Bye bye.
You.